Jnanam paramam dheyam. Knowledge is supreme.
So, we continue our discussion of this symmetry of normal modes of a D3H molecule with 4 atoms, and so far we have reached this situation where for C3 we have a 12 by 12 matrix and the character is 0. Okay. Why is it 0? Because this minus of exactly offsets plus 1. But we have actually learned something very, very important from this exercise. What is it that we have learned? You see, these blue blocks are what we had worked out, right, from the coordinates initially. What is this one? This is the contribution of coordinates of atom 2 in atom 1, okay. Only the coordinates of atom 2 make a non-zero contribution to the transformed coordinates of atom 1. Why? Because atom 1 has moved from its original position to the position of the original position of 2. Only the coordinates of atom 1 make a non-zero contribution to the transformed coordinates of atom 3. Why? That is how the transformation has taken place. So, what we see is that if atoms change place, then the non-zero blocks actually go off diagonal, right. What is the only atom that has made some non-zero contribution to the character? Atom 4, the only atom that has not moved from its own position as a result of the transformation, right. This is something that is very, very important, and you see, to get this one matrix we have spent like half an hour. Now we are going to get the other matrices in a matter of 2-3 minutes each, okay. So, the important lesson that we have learned is that the off diagonal blocks, non-zero off diagonal blocks, are for atoms that change places and they do not contribute to chi, right. So, if you remember the old English proverb, a rolling stone gathers no moss, right. If atoms move from their own position as a result of a symmetry transformation, symmetry operation, then they do not contribute to the character. This is something that we learned, and this is something that we will use now. Things will become very, very simple, okay. Let us go to the next symmetry operation. Before that, is there any question at this stage? Let us move. C2, remember where C2 is? Where is C2? This is 1, this is 1, this is 1. Do they belong to the same class? C2s, do they belong to the same class? Yes. So, it is enough if we work with any one C2, okay. We choose to work with this C2 that goes to atoms 1 and 4, alright. Now, as a result of this C2, what will happen? Which atoms move from their original position? Yes, 3 and 2 will interchange, right. 1 and 4 remain in their own position. This is how the picture is going to be. So, I hope it is not very difficult to understand that 3 and 4 will make no contribution to the character. Only 1 and 4 will make contributions. First, second point is 1 and 4 will make equal contributions. Are we clear? 2 and 4 move from their original position, therefore, they do not contribute to the character. 1 and 4 remain in their position, therefore, they contribute equally to the character, okay. So, see, now the problem has become so simple. You do not have to work with 12 coordinates anymore, you only have to work with 3 coordinates, that is all. These are the coordinates, right. I hope you remember, this is x, this is y, this is z. So, tell me then what happens to x1 as a result of C2? What is x1 dash? Same. What is y1 dash as a result of C2 operation? Minus 1 is the character. What about z1 dash? It becomes minus, right. So, this is the transformation matrix I get. I do not worry about anything else. See, the only thing I worked out is this. For x1 we said there is no change, for y1 it becomes minus y1, for z1 it becomes minus z1. So, that block is 1 0 0 0 minus 1 0 0 0 minus 1, and you will have an identical block for atom 4, because atom 4 also does not move. Have we understood this matrix? Okay. Why do I not write the off diagonal blocks? Of course, there will be a similar block for 2 and 3 as well, but they will be off diagonal. So, I do not even write. The only thing I want is character. What is the character then? 2. Chi of C2 is minus 2. Alright, C2 is done. What is next? Let us do sigma H. For sigma H, which are the atoms that move from their position? None. Does that mean we have to work with 12 coordinates? No. Why not? Yes, because all 4 will make identical contribution. Just work out any one. Okay. So, sigma H is very easy, isn't it? X1, what does X1 become? What is sigma H? It is the xy plane. Z is your C3 axis. So, what happens to X? Same. What happens to Y? What about Z? Minus 1. So, what is the contribution to character of each atom? 1 plus 1 minus 1. So, it is 1. Maybe you are giving me the answer when you said 1. I thought you were giving me the answer for X only anyway. And how many such blocks are there? So, what is the character? Character of sigma H is 4. S3, what happens when I do S3? S3 is similar to C3 in that 1, 2 and 3 interchange places, 4 remains this, 4 remains in its own place. What is the only difference? You are doing an additional reflection. So, Z will become minus Z, that is all. Okay. So, what is it then? This is the only block you have to worry about. From X and Y you know already, you will get minus half minus half. For Z you are earlier getting plus 1, now you will get minus 1. So, minus half minus half minus 1 minus 2. Okay. Sigma V is Zx, right? Sigma V is Zx. Of course, I could have taken this one, but it is more convenient if I take this. So, I will take this. Sigma V is Zx. So, what will happen to X? So, first of all, wait, when I apply sigma V, which atoms remain in their place, which atoms move from their place? Again 2 and 4 interchange places, so they do not matter anymore. 1 and 4 will only matter, and they will make identical contributions. Okay. So, what will happen? What will happen to X? This is X, this is sigma V. Will it change? No. So, character is 1, sorry, coefficient is 1. Y, will it change? Where is, yeah, Y will become minus Y. Yeah. And Z, same. So, what will the character be for each atom? 1, 1, minus 1, that is again plus 1, right. See, X remains same, Zx, Z also remains same, 1 plus 1 2, and Y becomes minus Y. Yeah, did not even watch. So, 1 plus minus 1, that is 1. How many atoms contribute? 2. So, 2 into 1 is 2. This. Simple. So, finally, after doing all this, this is where we are. This is the representation we have got, right, using the 3n Cartesian coordinates. Do you think this is an irreducible representation? Of course, how do you know? Unless I show you the character table. This is the character table of D3H. Do you see any 12-dimensional representation? No, right? You have 1, 2, 3, 4 one-dimensional representations, and you have 2 two-dimensional representations, right? So, there is no 12-dimensional irreducible representation associated with D3H point group, right? Which means, well, which means what is written here? It is a reducible representation, okay. And just to remind ourselves once again, this reducible representation, what is the basis for this reducible representation? The 3n coordinates. 3n coordinates, out of which 3 should be rotational, 3 should be translational. Remaining 3n minus 6 are your vibrational coordinates, okay. What do I do now? I have to break down this reducible representation into its constituent irreducible representations. How do I do that? To do that, what we do is we again invoke what we had written, great orthogonality theorem, okay. What was great orthogonality theorem once again? Not the mathematical expression, but the philosophy. What did great orthogonality theorem tell us? That these matrix elements of transformation matrices behave like members of a set of orthonormal vectors, right. They form an orthonormal set, right. So, from there we had written some 5 rules, one of which was chi I r, chi j r, if you multiply them and sum over all r, then you get a 0, and if you sum over chi I of r multiplied by chi I of r, then what do you get? What is this? H. What is H? Order of the group, which is total number of symmetry operations, not elements, operations. We know this, right, and this is why we say that they behave like a set of orthonormal vectors. This is the condition of orthogonality, this is the normalization condition, okay, right. Let us see if this will help us derive a very simple formula, mathematical expression, by which we can conveniently break down any given reducible representation into its constituent irreducible representations. Let us see. Let for a reducible representation, let us say for some symmetry operation R, the character is chi of R, okay. So, what we are saying is this is chi of E, this is chi of C3, this minus 2 is chi of C2, 4 is chi of sigma h, and so on and so forth, okay. If it is a reducible representation, so let me give that a name. For reducible representation gamma, this is what it is. If it is a reducible representation, I should be able to write gamma as sum over I gamma I, right, where gamma i's are the irreducible representation, gamma I is the ith irreducible representation, I is a general identifier, okay. So, it is something like, sorry, I made a mistake here, I will write like this, ai gamma I, there has to be a coefficient also, okay. What does that mean? If I go back to the character table, what are the gamma i's? This, right. So, what I am trying to say is this, I should be able to write something like, for any gamma, I should be able to write A1 multiplied by A1 dash plus A2 multiplied by A2 dash plus A3 multiplied by, or well, I can in fact write like this, A1 small a1, no, let us leave it like this, A3 multiplied by E dash plus A4 multiplied by A1 double dash plus A5 multiplied by A2 double dash plus A6 multiplied by E double dash. Are we clear what we are trying to do here? Any reducible representation should be a linear combination of the irreducible representations. So, the reducible representation that we have, the 12, 0, so on and so forth, we should be able to write it as a linear sum like this. So, our job at hand is, can we have a way of finding the values of A1, A2, A3 and so on and so forth. Are we clear? So, this is the general expression, gamma is equal to gamma I, AI gamma I. Can you tell me how I will be able to write chi of R in that case? Chi of R is the character for the symmetry operation R in the reducible representation. What will be the expression for chi of R? Starting from here. I will write it, see if that makes sense. Sum over I, AI, chi I of R. Does this make sense? What is chi I of R? Let us say we are talking about the C2 dashed symmetry operation. These are the chi I's of R. Okay? In the reducible representation, whatever character I have for C2 dash should be a linear sum of this 1, minus 1, 0, 1, minus 1, 0. Does that make sense? Right? Why? Because the reducible representation itself is a linear sum of the irreducible representations. Does this make sense? Chi of R is a linear sum of the characters of that symmetry operation R in the different irreducible representations. If there is a doubt, this is the time to ask. For every R, are the coefficients the same? This is the question that should come to our mind. Yes, it is. Yes, it is. That is what we are trying to say, right? When we write this gamma equal to sum over I, AI gamma I, what we mean is that for no matter which R you take, the same linear combination should hold. It cannot be different for different R's, because then you will not get the same reducible representation. Okay, that is the question I was actually waiting for. Great. Now we will go ahead. Now see, chi R, and what I will do is, to make things perhaps a little easier to understand, I will expand the linear combination on the right hand side. I will write like this: A1 chi 1 R. You will understand in a while why I have left a space between A1 and chi 1 R, plus A2 chi 2 R, plus so on and so forth, plus let us say take some specific one, AJ chi j R, plus what will be the last one? It does not matter, we will write like this. Okay, this is what it is. So, what is a very common technique that we use all the time in quantum mechanics? When we have linear sums and all, and we have to simplify it, make a big expression small, there is some common trick that we use all the time. Yes. So, how do we do that? We left multiply by one of these vectors and then sum over. What we will do is, we will left multiply by say this one, chi j R. So, write that. Okay, I have just left multiply, done nothing else. Now I will complete the trick. What should I do? Sum over all R, right? alright. So, see what is this one? Sum over R, this is written very badly, chi j R, chi 1 R. J is not equal to 1, right? J is some other number. So, sum over R, chi j R, chi 1 R, what is that? 0, right? So, this is equal to 0. What about this? 0. What about this? H, and everything else is 0, isn't it? So, what I have then is I have sum over R, chi j R, chi R is equal to Aj into H, or if I want to write in terms of Aj is equal to 1 by H sum over R chi j R chi R. What is Aj? Aj is the coefficient of the jth irreducible representation. What is chi j of R? It is the character for symmetry operation R in the jth irreducible representation. What is chi of R? It is the character of the same symmetry operation R in the reducible representation. Okay. So, now see, we already know the values of chi of R, right? 12 0 minus 2 4 minus 2 2, and if I look at the character table, I also know the values of all chi j R's, is that right? So, we can find out the values of Aj's for all J's, okay? You just have to work it out. Yes, okay. Chi is character. So, if I only write chi of R you have understood? Okay. Chi j R means, let us see, 1 2 3, see E dash, that for that j equal to 3. If I choose the symmetry operation sigma h, then chi j R for sigma h for E dash is 2. So, chi j of R is the character of the symmetry operation R in the jth irreducible representation. Now, I want some answers. Homework, you have this character table D3H, you have this reducible representation, and you have this rather simple mathematical expression by which you can decompose, or maybe again I will resort to dramatics a little bit, by which you can reduce the reducible representation into its constituent irreducible representations that cannot be reduced any further, right. So, please do that for homework, okay. Work out the values of Aj, and that is where we will start from next day, right. Thanks.